I welcome you all for the metal forming part 2 lecture. This section we are going to discuss about the gate previous year gate question and answers. First question is match with metal forming process and type of stress. First one is coining, wire drawing, blanking, deep drawing. Other side tensile, shear, tensile and compressive. So for this the answer is A. That is coining is due to compression and wire drawing is for tension. Blanking is for shearing. Deep drawing by means of tensile and compressive. Next question is a problem. Calculate the punch size in mm for a circular blank operation for which details are given below. Size of blank 25 mm, thickness of sheet 2 mm, radial clearance between punch and die 0.06 mm, die allowance 0.05 mm. Now we will work out the problem. Given is size of blank, that is D. Capital D is given, that is 25 mm. Thickness, which is equal to 2 mm. 2 mm is the thickness. And the clearance, radial clearance between punch and die, that is C, which is equal to 0.06 mm. Allowance, that is A equal to 0.05 mm. Now we have to calculate the what we want to calculate, punch size. Okay. So punch size, which is in diameter, which is equal to D. Capital D minus 2C minus A, that is 25 into 2 into 0.06 minus 0.05. So we will get 24.83 mm. Now the answer is A. Next question is, the maximum possible draft in cold rolling of sheet metal increases with increase in coefficient of friction, decrease in coefficient of friction, decrease in roll radius, increase in roll velocity. Here, the relation for rolling is given by F equal to mp, where m is the coefficient of friction, F is the tangential force, P is the normal force between the roll and workpiece. From this, increase in m, the draft in cold rolling of sheet metal increases. So while increasing the draft, okay, the maximum possible draft in cold rolling of sheet metal increases with increasing coefficient of friction. Answer is A. The next one is a problem. In a single pass rolling process using 410 mm diameter steel rolls, a strip of width 140 mm and thickness 8 mm undergoes 10% reduction of thickness. The angle of bite in radius is, so in radius we want to find the angle. So first we draw the diagram so that it will be easy to understand. Remaining is R minus Y. This is also Y. And this is also thickness 2. This is thickness 1. Okay. So here we will get theta, right? So from this diameter equal to 4 10 mm. From this radius equal to 205 mm. Thickness 8 mm. Okay. In question, they gave the reduction of thickness. Reduction of thickness is 10%. Okay. So that we will take it as the reduction thickness. Right. 10%. That is y equal to. So this 10% is 10 by 100 into the thickness is 8. So it is 0.8 mm. Okay. So y can be calculated as reduction thickness divided by 2. Okay. 0.4 mm. So from this diagram, from triangle OPQ. So this is OPQ. From this triangle OPQ, cos theta equal to r minus y divided by r, which is equal to 205 minus y is 0.4 divided by 205, which is equal to 0.99804. So we have use here. So we have the triangle like this, OPQ. So this is r, this is theta, r minus y. From that we can calculate the cos theta. So now theta equal to cos inverse of 0.9984, which is equal to 3.58. So in question they are asking angle of bite in radians. Okay, angle of bite in radians we want. So we can simply multiply the answer by 1 by simply multiply the answer by pi by 180. So we will get the radians, which is equal to 0.062 radians. So this is what the answer, the angle of bite. So answer is C. Next one is in rolling process, the maximum possible draft defined as the difference between the initial and final thickness of metal sheet mainly depends on which pair of the following parameters: strain, strength of work material, roll diameter, roll velocity, coefficient of friction between roll and workpiece. So we have a maximum draft formula, that is del H equal to mu square R. Mu is the coefficient of friction between roll and work. R is the radius of roll. From this, so roll diameter and coefficient of friction between roll is the right answer. So answer is D, R and T. Okay. So this is del H equal to mu square R. Right. Then next one is the problem. A strip thickness 40 mm is to be rolled to thickness of 20 mm using a 2-high mill having rolls diameter 200 mm, coefficient of friction and arc length in mm respectively odd. So we want to know the coefficient of friction and arc length in mm. So given us thickness 40 mm, rolled thickness. So we will take thickness h1 equal to 40 mm, h2 equal to 20 mm. Okay, then roller diameter is 200 mm. So obviously radius will be 100 mm. Okay, now we want to know the arc length and coefficient of friction. So we have the formula projected length projector length, which is equal to L equal to root of R into del H. Del H equal to H1 minus H2, initial minus final thickness 20, which is equal to 20. So all this 100 into 20. So we'll get L is 44.72 mm. Okay. Now we found the arc length. We want to know the coefficient of friction. Okay. So coefficient of friction, we have formula del H, which is equal to mu square R, maximum draft formula. So del H we know 20, mu we have to identify, which is 100. So from that we can get that is mu equal to 0.4472. So mu equal to 0.4472, and this is projectile length is 44.72. So this is what the right answer. 0.447 is 0.45, that is coefficient of friction. Then the draft length is 44.72. This is what the right answer. Next question is the cold forming process in which a hardened tool is pressed against a workpiece when there is a relative motion between the tool and workpiece to produce roughed surface with regular pattern. Thus, roll forming, strip rolling, knurling, chamfering. The right answer is knurling. The thickness of sheet is reduced by rolling without any change in width using 600 mm diameter rolls. Neglect elastic deformation of the rolls and assume that the coefficient of friction at the roll of workpiece interface is 0.05. The sheet enters the rolling rolls unaided. If the initial sheet thickness is 2 mm, the minimum possible final thickness that can be produced by this process in a single pass that we have to calculate. So given is diameter, which is equal to 600 mm. So radius is 300 mm. Coefficient of friction 0.05 and H1 equal to 2 mm and H2 we want to calculate. This is what the given. So we have equation del H equal to mu square R. So H1 minus H2 equal to mu square R. H1 is 2 minus H2 0.05, that whole square into R is 300. From this we can calculate the H value, which is 1.25 mm. Okay. The minimum possible final thickness. Okay, the minimum possible final thickness they are asking. So that is H2 equal to 1.25 mm. In a rolling operation using rolls of diameter 500 mm, if a 25 mm thick plate cannot be reduced to less than 20 mm in one pass, the coefficient of friction between the rolls and the plate is. That is what they are asking. Here, diameter is 500 mm, radius is 250 mm. Then thickness of plate, that is H1 is initial thickness, is 25 mm. That cannot be reduced less than 25 mm. Okay, that's we are taking as 20. So from that they are asking the coefficient of friction. This is what they are asking. Given data, these are the given data. Then we have the formula del H equal to mu square R. So H1 minus H2 equal to mu square R. That is 25 minus 20. Mu square we don't know. R is 250. So from that we can calculate. This is 5, which is equal to mu square into 250. So 5 by 250. Then mu is, we have to find the mu value. So we have to find the mu value. That is mu is 0.141. The operation in which oil is permeated into pores of powder metallurgy product is known as impregation. If the pores in a sintered compact are filled with an oil, the operation is called impregation. The lubricants are added to the porous bearing, gears, and pumps, rotors, etc. In powder metallurgy, the operation is carried out to improve the bearing property of bush is called this impregation. In two-stage wire drawing operation, the fractional reduction ratio of change in cross-sectional area to initial cross-sectional area. In the first stage is 0.4. The fractional reduction in the second stage is 0.3. The overall fractional reduction is, so initial cross-sectional area, initial reduction cross-sectional area is 0.4. Then second stage cross-sectional area is 0.3. From that we have to calculate the overall fractional reduction. So this initial is A0 minus A1 divided by A0, which is equal to 0.4. So second stage equal to 0.3. So this can be written as 1 minus A1 divided by A0, which is equal to 0.4. So A1 by A0, which is equal to 0.6. In the same manner, 1 minus A2 by A1, which is equal to 0.3. So A2 by A1 equal to 0.7. So now we want to know the overall frictional reduction. Then we have to calculate, that is A0 minus A2 divided by A0, which is equal to 1 minus A2 divided by A0. So this one A2 divided by A0, that can be written as A1 by A0 into A2 divided by A1, which is equal to 1 minus A1 by A0, A1 by A0 equal to 0.6, A2 by A1 equal to 0.7. That we have to substitute here. 0.6 into 0.7. From that we can get 0.58. So overall fractional reduction is 0.58. Okay. The next question is 10 mm deep cylinder cup with a diameter of 15 mm is drawn from a circular blank. Neglecting the variation in the sheet thickness, the diameter of the blank is. Okay. So given is diameter of the blank and height also they gave 10 mm. This cup diameter. Now we want to know the diameter of the blank. Okay. So D equal to root of D squared plus 4 DH. Let us ask substitution only. 4 into 15 into 10. So we can get 28.72 mm. So this is what the die of blank. Okay. The next question is a regular hole of size 100 mm into 50 mm is to be. Next question is a rectangular hole of size 100 into 50 mm is to be made on 5 mm thick sheet of steel having ultimate tensile strength and shear strength of 500 megapascal and 300 megapascal respectively. The hole is made by punching process. Neglect the effect of clearance, the punching forces. So we want to know the punching force. So given is rectangular hole size which is equal to 100 into 50 mm square. Then thickness is given 5 mm. Tensile strength which is equal to 500 megapascal. Then shear strength also given which is equal to 300 megapascal. So we know that punching force which is equal to L T into tau. So here perimeter L equal to 2 into 100 plus 50 which is equal to 300 mm. So the punching force F which is 300 into thickness is 5 mm and tertiary shear strength that is 300. So it is 450 kilonewton. So they are asking in kilonewton. The answer is B. The next question is in rolling process, the state of stress of the metallurgical undergoing deformation is this pure compression, pure shear, compression and shear, tension and shear. So normally rolling process just compression only. Okay, two rollers are rotating in opposite direction. So it is compression only. So it is pure compression. Most metal rolling operation are similar in that the work material is plastically deformed by compression force between two constantly spinning rolls. Thus, in a rolling process, the material undergoes deformation in the state of pure biaxial compression. So, it is pure biaxial compression. The next one is match. Match the following product with preferred manufacturing processes. One side is product, another side is process. Rails, engine crankshaft, aluminum channel, PET water bottle. Process, blow molding, extrusion, forging, rolling. So here P is for that is rails. Rail is by means of rolling process. Then engine crankshaft is forging. Aluminum channels or extrusion process. Then PET water bottles by means of blow molding. So answer is B. Blow molding is a manufacturing process by which hollow plastic pots are formed. Example, PET water bottles. Extrusion is the process used to create object of fixed cross-section profile. A material is pushed or pulled through a die of desired cross-section, such as aluminum channel. Forging is a manufacturing process involving the shaping of metal using localized compressive force. Example is engine crankshaft. Rolling is a forming process in which metal stock is passed through one or more pairs of rows. That is rails. The next question is the problem. A brass billet is to be extruded from its initial diameter of 100 mm to final diameter of 50 mm. The working temperature of 700 degrees Celsius and extrusion constant is 250 megapascal. The force required for extrusion that we have to calculate. First, we will write the given. Given is initial diameter 100 mm and final diameter 50 mm. Then temperature is 700 degrees Celsius. Then constant 250 megapascal. So we want to know the force required for extrusion. So this is extrusion force F equal to KA naught on A naught divided by AF, that is initial to the final. Initial area divided by final area. So initial diameter will get this final diameter. So this we can write this. So we know that A equal to pi by 4 d square. So K equal to A naught into pi by 4, that is initial area, 100 square, pi by 4 into 100 square divided by pi by 4 into 50 square, which is equal to this will be cancelled. So we are getting 4 here. Then finally we will get 2.72 meganewton. Okay, this is the extrusion force. So these are the reference book. So far we discussed about the different questions asked in the previous year. Happy learning. Thank you.